All right, so here's another video talking about working through more advanced questions in statistics. All right. So a company manufactures model rockets that require igniters to launch. Once an igniter is used to launch a rocket, the igniter cannot be reused. Sometimes an igniter fails to operate correctly, and the rocket does not launch. The company estimates that the overall failure rate, defined as the percent of all igniters that fail to operate correctly, is 15%. Now, a company engineer, they develop this new igniter, and they'll call it the super igniter, with the intent of lowering the failure rate, improving on the 15% failure rate. Now, to test the performance of the super igniters, the engineer uses the following process. All right, step one super igniter is selected at random and used in a rocket. Step two, if the rocket launches, another super igniter is selected at random and used in a rocket. Step two is repeated until the process stops. The process stops when a super igniter fails to operate correctly, or 32 super igniters have successfully launched rockets, whichever comes first. So if we get to 32 successes without a failure, well then, that's going to be good enough. Now, assume that the super igniter failures are independent, to simplify our work. So, if the failure rate of the super igniters is 15%, what is the probability that the first 30 super igniters selected using the testing process successfully launch rockets? All right. So notation can help us out here. Go ahead and pause the video, try it out on your own, and then feel free to unpause when you're ready to check. So let's have a random variable x. X is not geometric, right? We're not looking to see when does this first failure occur, right? In which case a failure is a success, right? But rather this is a binomial variable that we can think of, right? Where the binomial, we have a fixed number of trials, 30. We have a probability of success, that is failing to ignite, 0.15. We have our independent events, and we also have either it ignites or it does not. So what's the probability that no failures? Well, that would mean succeeding every time. So 0.85 raised to the 30th power, that's about 0.0076. So a fairly small number. Now, you might be able to find this quickly on your calculator, but it is very, very important that at the very least, all right, very, very important, at the very least, you show the formula as to how you got to your answer to be able to get full credit. Okay. Next, if the failure rate of the super igniters is 15%, why is it not possible to assert that the sampling distribution of the sample proportion failure rate for a random sample of 30 super igniters is approximately normal, with the mean proportion of 0.15 and the standard deviation of the sample proportion given by the square root of p times 1 minus p all over n? Think about what that reasoning would be. Pause the video. Unpause when you're ready to check. Okay, well, one, we don't know if the 10% condition is met for independence. However, it doesn't really matter about the 10% condition because the 10% condition is for independence. What matters for us is, are we approximately normal from this binomial situation, which we can express as a proportion? And that means we need to check our large counts condition. And our large counts condition is not met. From 30 trials, right, we expect to see 4.5, I believe it would be. We expect to see 4.5 failures. Well, that's not greater than or equal to 10. Right? I need to have both my successes and my failures be at least 10 if my sampling distribution of my sample proportion, in this case, the failure rate, is going to be approximately normal. If I don't have that large counts condition met, that sampling distribution of a sample proportion cannot be said to be approximately normal without looking at the distribution. Okay. Next, given that the first 30 superigniters do successfully launch rockets, what is the probability that the first failure occurs on the 31st or the 32nd superigniter tested if the failure rate of the superigniters is 15%? Think about how you would answer that question. Pause the video, then unpause and check your response. Well, now I'm going to define a new variable y, because previously I used x, and this variable is going to be geometric. And it's going to be geometric because I'm looking to see my first failure, which I could think about similarly as my first success. Right? When does this happen for the first time? Well, that's geometric, and I have my probability of failing, which I'll say is a success. And that is, probability is 0.15. So I'm looking for the probability of the failure occurring on the first or the second time, right? I've already had 30 successes, but those have no effect on my next ones because my trials are independent, right? I'm not due a failure. No, each trial is independent. So 31st or 32nd? Well, that's saying does it occur on the first one after 30 or the second one after 30? Right? Well, does it occur on the first one after 30? That's a 0.15 chance of happening. Or does it occur on the second one? So that means don't fail and then fail. So if I add these two probabilities together, then I get to my correct answer. All right? Once again, you must either have your work or your notation. You've got to have one of these along with the correct answer if you're going to receive full credit. Okay. Yes, many of you could do this in your head, type the numbers into the calculator and have the answer right out without troubles. But it's important to show how you're approaching it. Okay. And finally, the last question. Given that the first 30 superigniters successfully launch rockets, is it reasonable to believe that the failure rate of the superigniters is less than 15%? Once again, pause the video, think about it, unpause when you're ready. So, the probability of no failures in 30 trials with the failure rate of 0.15 is 0.0076. All right, we got that value from part A. I don't need to go back and show how I got it again. I got it from part A. Now, since that probability is less than our standard of 0.05, our significance level of 5%, then it is reasonable to believe that the rate is less. You should always have context. You should always have reasoning. Okay. So that goes as a way of looking at distributions and how different areas of statistics come together. Once again, this question came from one of the released AP exam problems. Right, but there are some little additional pieces and little tweaks between what was provided on the AP exam and what we're asking you to consider. And being able to do that well is a key for this course. Thank you very much for your time. Have a great day.